Good morning, everyone. How are you doing this morning?
Good morning.
Good morning. Hi.
Hi, Professor.
Good morning.
Okay, so let me go ahead and share the screen with you. All right, just a reminder again, I welcome you to turn on your camera. You can turn it off whenever you need to. All right, so to pick up where we left off, we started talking about representing vectors in two different directions. The reason to do that little bit of math, because we want to be able to analyze motion in 2D, right? So if you have something moving in the both horizontal and vertical directions, so it's kind of going like this, that's motion in two different directions. So just to start out with a question, you can totally answer this using your intuition and your experience. So if you're playing darts, what would you do normally in order to hit the center of the target? So I'm gonna go ahead and just give you this question to vote. Doesn't take too much thought, just basically whatever your intuition tells you. All right, do I have everybody's vote, your prediction, your thoughts from the experience? Any last minute vote? Okay. All right, let's take a look. So normally when we play darts, in order to get to the center, a lot of you guys voted for aim a little bit higher, not directly toward the center, but aim a little bit higher because the dart will fall a little. Yes, that is my experience as well, although that doesn't mean I can hit the center. I'm still not very good at it. But that is the something that we can trust our common sense, our intuition in terms of the motion, the parabolic motion. The dart will fall because of the gravitational pull of the earth, right? So if you wanted to hit the center, you wanted to be able to aim a little bit higher so that you are taking that fall into consideration. Okay, so yes, so B is the correct answer. I wanted to get some idea that some people might vote for A, that I just want to see what might be a reason to vote for A. I do have a guess at the reason, but I just want to hear that. What are your thoughts? Is there any place at aiming where we are actually aiming it directly at the center of the target?
I voted for B, but I kind of thought of something for A I thought might be interesting. If you're obviously we're human, so we can't do this, but if you were throwing it fast enough, like really, really, really fast, that it wouldn't measurably go any down, but it moved a lot horizontally, then I guess you could throw it directly, but we can't do that. So because we're the ones playing darts in this example.
Thank you, Juan. I appreciate the thought. Yeah. So you're thinking about if we shoot the dart super fast, where the fall can be negligible during that time, then maybe you can aim it directly. Yeah, I think that's absolutely reasonable. Yes, so if we could do that, it's not going to have a reasonable a fall that you can even notice, and then you can just throw it directly. I also want to say A is also a pretty good guess, because we do I don't know if you have any other experience like you shooting a gun or something. You do aim directly at the center, so you might wonder then, what are we doing there? Does that mean our bullet is fast enough? We don't have to consider the fall. So the reason for that is we do consider the fall. I want to show you this picture. Is it has already been sort of designed in such a way that when you look at the green line, right, you are looking into the target directly at a straight line, but the design of the gun or whatever device you're using have already considered the fall of the object. So it's kind of shooting it slightly upward, and eventually will be able to fall a little so you can still reach your target. But that doesn't mean that the bullet doesn't fall. It does. It does still obey the law of physics. Yes, and Jose said it is called zeroing a scope. Very good, very good. Okay, so with that in mind, I wanted to ask you guys another question. This one we don't have any experience doing, but we can rely on sort of the analogy of the dart. Let's say you're a vet trying to launch a tranquilizer dart into a monkey. The monkey is hanging from the branch right now. As soon as the dart is launched, the monkey let go. So these two are happening at the same time. And what happens? So let's say the dart is now aimed directly at the monkey at the moment. But as soon as we fired the dart, the monkey let go. Will you be able to hit the monkey? Assume the monkey is well within the range. Obviously, if you're too far away, you cannot. Nothing you can do. But we'll assume the monkey is within your range. Do you think your dart will hit the monkey, or would it miss the monkey, or would it depend? Now, for this one, I will give you a couple minutes to discuss with others. And when we come back, we can vote. All right. So feel free to take a screenshot of the picture before you join the breakout room invitation. Okay, please put in your vote. We will go for another 10 seconds. The clock will run for another 10 seconds. All right, any last minute vote? Any other votes? All right, okay, so I will go ahead and close this. All right, so here is the results. Anybody would like to talk a little bit about the reasoning process? Whether the dart will hit the monkey or miss the monkey, or would it depend on the V0? Any thoughts?
The way I kind of thought about it was kind of going back to Juan's analogy about like, if we're human, we can't throw something as far, but since this is dealing with machinery, then if its initial value is going at a speed faster, like at a really high speed, then it'd be probably able to hit the monkey in time.
Okay, so would you say, let's say before the monkey let go. So this situation is you're trying to hit the monkey and you're trying to aim your dart directly at it. And if the monkey didn't let go, do you think the dart would have hit the monkey? Not think about the gun. Here, let's not think about the gun where it kind of already had that fall built in. Here, you're just treating this dart as a dart, like you're playing darts. If the monkey did not let go, do you think the dart will fly in a straight line like I draw it here? And let's say you were aiming at the arm of the monkey at first, the arm. Okay, if the monkey did not let go, do you think the dart will go straight as a straight line and hit the monkey's arm?
It would hit lower.
Would hit lower. Very good, because the dart would fall down, right? So, and in this case, monkey sees you and then let go as soon as the dart is falling. So, do you think the dart would hit the monkey? Because the monkey is trying to, get away from it, obviously. What would happen in this case? I see a lot of the answer voted for B. It's the monkey if V0 is large enough. Would anybody be able to talk a little bit about the reasoning for choice B?
For me, I chose B because of the previous example with the gun. So if that's where you're aimed, then that's where it's gonna end up, but there's gonna be a drop. Like I assumed the thing would go like up and down kind of thing. So
okay, so what did you say would go up and down?
The dart, so the scope, I kind of took it as like the scope would be looking right at the monkey, and then the dart would have to go like higher and then drop if it were going to hit the arm kind of thing. But
okay, so you're saying the trajectory is kind of like a parabolic trajectory, right?
yeah,
I see. Okay, so the dart would kind of go like this. All right, I agree. And why would the velocity need to be large enough in order to hit the monkey? Do you think the choice is B?
well, I thought I was debating between A and B, but I chose B because if the dart ends up where I'm looking, then I thought that like if it took too much time, then the monkey would be gone basically.
Yes, okay, very good. So the reason that I added the one, you're right, that obviously if B is too small, you will shoot it and it will fall down right away, right? The monkey would not even, you're not even close as a monkey. So that's why we added an extra sentence saying, assume the monkey is within the range. So that sort of already taken care of the velocity being big enough. So if we have that assumption that monkey is within the range, then we actually will be able to hit the monkey regardless of the specific value of V0. But you're right, we do want V0 to be within the range. But having that assumption met, we can always hit the monkey. So let's see a demonstration of this, and then we can break it down to see why that is. So let's watch this.
Grammarly helps you work
video.
more efficiently,
Just 1 second.
which makes accomplishing your work goals easier.
Okay, let me switch my screen to our demo. Okay, I know that I will let you know it's going to be very fast, but eventually they will do a slow motion and you can see it. So there is a sensor just to make sure that once the ball is shot, triggers the sensor and the monkey is also let go. So simulate the example we were just talking about. So one is shot and one is let go at the same time. Okay, I don't know if you see the first one, but the slow motion showing that the ball actually does hit the monkey. All right, so let me bring everything back to the previous slide. So there's another demo that you can watch on your own. I'm not going to show all of it. But the answer is A. It will hit the monkey regardless of the value of V naught. Let's see how this breaks down in sort of a, I'll show a little animation to show you how it works. So if in this case, the dart is aiming horizontally, and then we will see the one that is aiming upward. Then the monkey let go at the same time. Let's look at the motion of both of them. The dart in the horizontal motion is a constant velocity, right? It's shot with some velocity and keeping with that same initial velocity in the horizontal direction. In the vertical direction, it is a free fall. It is a constant acceleration in the downward direction with 9.8 meters per second squared, right? So you have the second equation describing the displacement of the dart in the vertical direction. The monkey, if the monkey let go, the monkey's horizontal position doesn't change. It doesn't go left or right, but it just simply falling straight down. So what happens is you can see that as the dart is going in the parabolic curve, the vertical velocity of the dart and the monkey are always keeping up with each other because those two are the same velocity. So you can see eventually once the dart reached to the other side, the monkey also dropped down to the bottom and they meet, right? So the dart hits the monkey. So let's look at if you are shooting the dart a little bit upward. So what happens here is you can see that is an initial velocity. We can break it down into the X and Y component. We look at the velocity in the X and Y component separately. That's what we're going to do solving these type of problems. The X component doesn't change. The Y component getting smaller and smaller because it's going upward, right? It's being dragged down by gravity. So you can see eventually the dart is here at this top of the parabola and then going to fall down, eventually will hit the monkey. This is assuming this is within the range of the dart. Okay, so now I wanted to talk a little bit about how do we analyze the 2D motion by looking at X and Y components separately. Before we do that, just a little trick refresher is remembering which one is the sine or cosine or tangent using SOHCAHTOA, because if we have a velocity v naught that is shot in the hypotenuse direction, and we need to know the v naught x and v naught y, we need to break it down into the x and y component using SOHCAHTOA. And we will analyze the motion in two different directions separately. I'll slow down and sort of write a little bit of that derivation for you. So let me switch back to my writing. Just 1 second, please. Okay, so let's see if we have an x and y component. 1 second. So let's say this is your velocity v naught. Okay, and this is my x direction and this is my y direction. What I would do is I will decompose this velocity into x and y component. Okay, so this is your x direction, v naught component, v naught x, and the vertical one is v naught y. So which means the original v naught is equivalent to having the v naught x and v naught y draw separately. Okay, so I'm going to, once I decompose this, I usually put little dash, 2 short lines on this v naught showing that I've already considered this. Okay, so using SOHCAHTOA, how is v naught x and v naught y related to v naught? Can you guys tell me? V naught x is v naught times what? Sine or cosine? Sine theta is the opposite over hypotenuse, which means v naught y is v naught times sine theta. Cosine theta is the adjacent, which is v naught x over v naught hypotenuse, which means v naught x is v naught times cosine theta. Okay, so that is good. So what we do is analyzing the motion of 2D. First of all, we define our x and y direction, define our coordinates, which already done. And then we will decompose our v naught into different direction, into x naught, into x and y components. And we have already done that as well, right? We did it here. And we had our coordinates defined here. And then the third step is now you're ready to analyze your motion in x and y separately. So let's look at the motion in x direction. What kind of motion is it in the x direction? Is it constant velocity? Or is it constant acceleration? Because that's the only two type of motion we had talked about, and we will do in this class. So the motion in x, is it constant velocity or constant acceleration?
Velocity.
Constant velocity, very good, because there is nothing slowing it down or speeding it up in the x direction, right? Your acceleration is only in the y. So which means the v naught, velocity in the x direction will always be whichever it start out with. Then obviously, if you want to know the displacement in the x direction is x naught plus v naught x times the total time. So this velocity times time give you the distance it travels. So you will know which equation to use in the x direction. Now if you analyze the motion in y, now the motion in y obviously would be a constant acceleration because you have the 9.8 meters per second, the little g pointing down at all times. And then you will use the two equations for constant acceleration, which is v in the y direction at any given moment is your v in the y direction, your initial velocity in the y direction plus your acceleration times time. Now, if you define your upward is positive, then your acceleration would be negative g, negative 9.8. You can plug that in. If you want to know your position in the y direction is your initial position in y or y naught, you can say y naught or y initial, plus your initial velocity in the y times time, plus 1/2 a t squared. So this is what we already derived in the previous class. We used x as a variable because now it's in the y direction. We want to be able to distinguish between the x and y different directions. That's why we are writing the symbol of position as in y. Okay, so it's just a variable. X and y is just really just a variable. Okay, so you can see you have horizontal, you have these equations in the horizontal, you have these equations in the vertical. Horizontal has no acceleration, right? Vertical, you have a 9.8 meters per second square downward for vertical, and you have different equations to use. All right, so are we ready? Are you guys ready now to solve more problems, more questions using these different equations? Before I move on, I want to ask any questions here? Any questions about the different component and the different equations we use in the x and y direction? Any questions so far?
Wait, why is the down arrow positive 9.8 and the up arrow negative g?
Yes, because g is only a magnitude. G is always positive, that's constant. It's simply describing the amount of the acceleration is 9.8. That's why I just say, well, g is this value and it's pointing downward. But in your coordinates, you have defined, if you wish, to be upward as a positive direction. So your acceleration in the scope of your definition is a negative number. That number is 9.8. So you can write g or you can write 9.8. Those two are equivalent. Does that make sense?
Oh yeah, thanks.
Thank you for the question. Very good. Now let's look at this one. We have two different objects. The purple ball is released from a height a meter above the ground. The blue ball is shot with a velocity horizontally, and it's sort of a follow a parabolic trajectory and falls to the ground from the same height. Which one will hit the floor first? Okay, we'll let you guys vote it here.
Professor, I have a question.
Yeah, go ahead.
If you can go back to the previous slide, the motion, oh, the one before that one, sorry. You said that the motion in y was constant acceleration. I was writing when you explained that and I kind of missed it. But when I look at the graph that you had earlier, it seems that velocity is constant. So, and you said that the velocity for the x component is constant velocity. So why isn't it the same for the y?
This the graph?
Lower.
This graph?
Oh, there, that one. We're explaining the v naught y.
Oh, v naught y is the initial velocity. I did not show what will evolve over time. Right? I only showed what happened initially. That's the v naught y. V naught y will, if you shoot it upward, obviously will decrease and decrease, just like how this is showing. This is your v naught y. And you see it's shorter now, right?
Mm-hmm.
And it's completely gone here. And then it's flipped direction going upward and bigger. Does that make sense?
Oh, okay.
Yeah, so it's not a constant, but thank you for that question. So v naught y is not a constant.
Thank you.
All right. Any more votes on this one? I'm sorry, I took the screen away, but here back have.
Professor, that's like the slide that we just passed. Was there any new information on that one? Because I think we skipped that if there was.
This one?
Oh, okay, no, that was just stuff we already wrote. Okay.
Yeah, it's just a summary of what I already went over. I would say this question, even though there are numbers to answer this question, you do not have to do any calculation. You should be able to just reason this conceptually. Okay, 10 more seconds, please. If you haven't voted already, please put in your prediction. Okay, I'm gonna go ahead and end this. All right, yes, very good. The choice answer for C is indeed correct. They will both hit the ground at the same time. You can try to calculate it, the time it takes, or you can simply reason. This is the motion in the y direction are identical between these two. One is being released from rest with an initial velocity of 0 and fall down for 1 meter. And other than the horizontal direction, the vertical direction is identical, right? If you just, we don't have to look at the horizontal direction because when we do the motion in the y direction, because these two are independent, right? Whatever it does in the y does not affect the x. So if they are falling all from the same height at the same time, of course, they will reach the ground at the same time. So the C is correct answer. Because of very similar to the monkey problem that we did previously. The follow-up question, we can use this follow-up question to demonstrate. I want to use this to demonstrate what we mean by analyzing the two different directions separately. So the question is, if the ball is being rolled off the table with some initial velocity, right? And it gone for a total distance of 0.8 meters away from the table and a fall for 1 meters. Can we use this information to find out how fast it rolled off the table? What is the velocity of the blue ball as it was rolling off the table? So, okay, so first, how do we solve a physics problem? The first step is to visualize the situation by drawing a picture. Here, the picture is already given. We could add to the picture and add our quantities and label them. So let's label the quantities of the information that were given about the blue ball, right? Obviously, right now we cared about the blue ball, so we don't have to draw anything for the purple. So let's say, okay, I wanted to be able to define my origin and coordinates. I'm just going to put my origin here. That is not unique. You can choose to put it elsewhere. But I thought it's convenient, simply put it here. I'm gonna say to my left is positive and upward is positive. It just seems to be easy to draw my coordinates that way. And again, that is not the only way to do this. You can probably put your origin here, that would be equally convenient. Okay, so any other quantities we can label? We know the initial velocity V naught, right? That is my initial moment as it falls to the ground. That is my final moment. So I know these quantities. In the x direction, my x initial is at the origin, so 0 meters. My x final is 0.8 meters, right? In the y direction, I have my y initial. Do I know y initial? So initially, you are at a height 1 meters above the origin. So my y initial is 1 meter. Y final is, what is my y final?
0.
0. You are at the ground eventually. So that is 0. Okay, so now let's see how we going to look at the motion x and y separately. Okay, I've done that. And what is the question I'm to try to solve for? The question is, what is the initial velocity in the x direction? So this is in the x direction. So V naught is also V naught x. It's in the x direction. I want to solve for this quantity. Okay, so what about the physics? We have already talked about the physics of the parabolic motion is the x direction is a constant velocity type of motion, and the y direction is constant acceleration. So let's look at the x first. So the information that's given to us, you might wonder, okay, which equation do I use? Well, you're given information about the position. So I'm going to use the equation that tells me about the position. Initial position plus velocity times time give you the final position because this is simply a constant velocity, right? Okay, so y initial is 0, I just said earlier. V naught x is what I want to solve for, question mark, times time. I don't know the time. And I know it traveled a 0.8 meters, so final is 0.8 meters. So you can see that in order to solve for V naught x, I need to find t, right? Okay, so but that's not all the information. I still have the y direction I have not used yet. So in the y direction, I have a constant acceleration type of motion, and I know what equations I should use. There are two equations, right? One about the velocity, one is about the acceleration. In that definition of my coordinates, my acceleration is downward, so that's negative 9.8 meters per second squared. So which equation would I be able, y final, v final in the y direction is the initial, okay, so let me say y final, y initial plus acceleration times time, right? That's the one of the equations. The other equation is y final is y initial plus v naught y t plus 1/2 at squared. These are generic equations for constant acceleration. So which one do I want that can solve for t? Well, this one has velocity in it. I don't know velocity. This one has position in it. I do know position, right? So I'm going to choose the second equation to use because I'm given information about the position. Plug in your position you got previously. Y final is 0. Y initial is 1 meter. The initial velocity in the y, what is this one?
0.
0, because it's rolled off in the horizontal direction. It has nothing in the y to begin with. So that's implicit. That's the implicit information that's already given to you. So this is 0. You don't have to consider this term. And negative 1/2, 9.8 meters per second times time. So this will give you the time. Time, you go ahead and solve it. It'll be 0.45 seconds. Plug it in back to this equation. Give you v naught x is 0.8 meters divided by 0.45 seconds. that is 1.78 meters per second. So you have solved this, right? You will say, okay, the ball will roll off the table at 1.78 meters per second. So you have solved it. So this is a demonstration of how you do X and Y separately. All right, let's look at this question is from your pre-lecture. I want to go through this very quickly because you have already done this. You have a red ball that's being shot directly upward, and you have a blue ball that's being shot at the angle 30 degrees above the horizontal direction with a double the velocity. Which one will go higher? So you can see that the height, which one will go higher, is asking your information for the horizontal direction or the vertical direction. Which direction is involved in terms of the height?
Vertical.
The vertical. So you're really asking about Y final position in the Y. So that is going to be solely determined about your velocity in the Y direction. Because if you shot up higher, faster, then you're going to go up higher. So this one is shot with V directly upward. And what about this one? This one is shot with VY by how much? So this is 2V, but we don't want this 2V. We want the component that is directly in the vertical direction. That's the vertical that is relevant here. So VY for the blue ball, VY initial is, so Katoya, remember it's hypotenuse times sine 30 or cosine 30. If I want this VY. Is it sine 30? Cosine 30. Guys?
Sine.
Sine 30. Very good. Sine 30 is actually 1/2. V2 times 1/2 is V. You can see that this was shot with V. This was shot with also V in the vertical direction. Then they will reach the same height because it's the same velocity up. It's going to reach the same height. Okay, 2 more bridge questions. Hopefully we can get through them. You have done this, I believe, previously in your pre-lecture bridge questions. Here we have 2 targets, and the 2 shells were fired with the same initial speed. So this information is same initial speed. So I'm going to draw the initial speed for both of them. This is fired here with some V0. This is fired with the same V0, just a different angle. You can see it's the same length of my arrow, but the angle is different. So which ship will get hit first? Any thoughts? What are your thoughts from the pre-lecture?
Second one.
Second one. And why is that?
There's less max height.
Less max height. You can think of the time it reached from the beginning. This is symmetric, right? It times goes from here to here at the same time going from here to here. So from the maximum height going down, the vertical direction is simply just falling from the maximum height. Now, if one has a bigger height, it's going to take longer to fall. The one with the smaller height will take a shorter time to fall. Very good. We could also analyze this by looking at the velocity graph, which is going to give me the same information. Now, I'm going to put some labels on it. So let's say this is the theta 1, right, that hit enemy 1. This is a different angle, theta 2, that hits enemy 2. So to calculate the total time it takes, because it's symmetric, I'm going to say from here to here, the time is T1. From here to here, the time is T2. So during those time, the velocity in the Y direction, target 1 is going to be Vy final is Vy initial plus acceleration is negative. I'm gonna define positive to be upward times T1. Okay, so at the highest point, what is your final velocity for the y direction? Y direction is that if you just simply throw it upward, reach the highest point, going down. So at the highest point, your y velocity is 0. Okay, we only have a horizontal velocity in this case, so that is 0. So you can see that you can calculate this t1. So y initial is going to be v naught sine theta 1, as we said, is equal to gt1. So t1 is v naught sine theta 1 over g. Likewise, t2 is v naught, same speed, but at a different angle, theta 2 over g. So theta 1 is bigger than theta 2, right? So sine theta 1 is bigger than sine theta 2 if they're both within 90 degrees. So sine theta 1 is always bigger than sine theta 2 if theta 1 is larger than theta 2. Now, which means T1 is sine theta 1 is bigger than T2. T1 is bigger than T2, which means it takes longer to reach the target 1 than it takes to reach target 2. So target 2 will get hit first, right? Shorter amount of time. So it's a shorter amount of time. Okay, so B is the correct answer. The last question, the second question for this bridge question. Now they're fired with different speed. So V1, V2 is different. I don't know which one is bigger. I don't need to know. I'm just going to draw them to show they're separate. And then they reach the different enemy ship, but they are reaching the same height. So now which one get hit first? Now I wanted to refer to the idea you come up with is if you can simply look at the height. Now, if they do reach the same height, the time it takes to go down from the same height is going to be the same time. So here is actually easier to analyze. The second half of the motion is from the highest point going down. In terms of your equations, is your y final is y initial plus, so here I'm gonna say is my initial, okay? At the ground is, at the ocean is your final. So this is what I choose to look at the second half of the fall, okay? So final initial plus v y initial times time plus 1/2 g negative 1/2 g squared gt squared. Your height is the same finally because they're all at the ground. Your initial height is all the same, is h. Initial velocity is 0 because they're falling from the highest point. So this is 0, 1/2 gt squared. So you can see this follows h is equal to 1/2 gt squared. If the same height, they have the same time because the height is the same, the time is also the same. The answers, they're both hit at the same time. You can see I use that the parabolic motion is simply symmetric. I ignored the first half of the motion. I focus on the second half. So you choose whichever half is easier or easier to calculate, depending on the question. All right, so that's all for today. This is the parabolic motion, and we look at x and y separately. Don't forget to, I believe we have, Monday is a holiday, Labor Day, so we don't have class on Monday. Next time I'll see you on Wednesday. All right, bye for now. Have a good long weekend. I'll see you guys next week.
Thank you, Professor.
Thank you, Professor. Bye.
Can you scroll up a little bit to the part where you found it was like the part where you found T. It was like a few problems ago.
Oh.
Right there.
This one.
Yeah. I just need that last piece.
Sure.
Okay, thank you.
Sure. Bye, everyone.
Professor,
Yes.
sorry, I had a question about acceleration. So I'm still a little bit confused about when you know it's negative and when it's positive, because for that particular problem that was asked earlier, you know how since we were going on a downward motion, it was still positive. So does it depend on whether if it's a free fall or not? Or sorry, I mean, I know that when it's free fall, it's going to be acceleration, but I just wanted to clarify that.
Yes, sure. Let me see if you could see my screen. You said there was one where we treat acceleration positive, and which one is it?
Could you scroll up a little bit, please?
Yeah.
It was right there. It's you know how you put plus y, but then you said that it would be negative.
Yeah, negative.
So then why
Because
would it be negative if it's going upwards?
Upward is what I want to consider to be a positive direction. So whichever is in the same direction as upward, that's what I consider to be, okay, upward is positive, but acceleration is down. So that's why acceleration is negative.
Oh, okay, I see.
You could totally reverse everything. Treat the downward is, let's see if we could do this. I say, okay, my ball is here. I want downward to be positive. You can do this. And this is still positive, okay? But the downward is positive. So what I would have labeled is y initial is 0, because this is the origin, you see? Here, I would say y final is 1 meter. Because from the origin, it's 1 meter. Then in that case, my A is positive because it's in the same direction as what I claim to be positive. This also works. So what we do is y final equals y initial plus 1/2 AT squared. So it's 1 equals 1/2 9.8 T squared. So you get the same result. Does that make sense?
Yeah. Yeah, so then when you flipped it, you'd have to change the x direction as well, right?
I don't have to. I can still choose my x to be to the left, but you could change your x to the right. So whichever you want is fine.
Okay.
Yeah, I don't have
Okay.
to flip my x and y at the same time.
Thank you.
Sure.
Oh, sorry, Professor. I was working on something and I figured out what I did wrong. Thank you. Have a good day.
Okay, have a good day. Bye.